On June 29th, astronomers announced the first evidence that the cosmos is humming with gravitational waves, ripples in the very fabric of space. This discovery was decades in the making. The signal of note is so faint that it's only warping space enough to change the distance between the Earth and the Moon by the width of a human hair. So, how in the world did we measure it? And what makes us so confident that what we're measuring is a gravitational wave background? Well, our gravitational wave detector is one like you've never seen, because it's galaxy-sized and made of exotic stars. Welcome back to Fringes. Even as someone who works on this stuff, this falls into the category of so crazy it just might work ideas. But it did work. Here, I'll show you the most important result. These are 15 years of data from the North American Nanohertz Observatory for Gravitational Waves. Pretty cool, huh? Look, I get it if you don't see what this graph has to do with gravitational waves. It's far from obvious. But I promise you that by the end of this video, you'll see how this graph holds secrets of gravitational waves, merging galaxies, and the biggest black holes in the universe. All you have to do is remember one little dance. In the last video, we learned how to dance like a gravitational wave. Specifically, we learned that if a gravitational wave is passing out of your computer screen in the forward-back direction, my body is warped in the perpendicular up, down, and left, right directions in this very specific way. We also learned that the goal of gravitational wave astronomy is to measure this motion. So to measure it, why don't we just get a really long ruler with a very fine scale and measure the changing shape of space that way? Alas, gravitational waves affect all matter they pass through, so our ruler would be dancing too. But what if we used something that isn't made of matter? Something that always travels at the same speed, regardless of where you are in the universe. Something like light. That is exactly what the Laser Interferometer Gravitational Wave Observatory does. LIGO's gravitational wave telescopes consist of two 2.5-mile long tunnels at right angles. Inside of these tunnels are 4 mirrors and 2 laser beams kept isolated from outside vibrations. LIGO measures the change in the time of flight of these laser beams, so that when a gravitational wave passes through the detector in the forward-back direction, the space between the mirrors in the up-down direction shrinks, then the left-right mirrors,
then the up-down mirrors, then the left-right mirrors, then the up-down mirrors, then the left-right mirrors, then the up-down mirrors.
Following the dance of gravitational waves. The gravitational waves that LIGO measures come from merging black holes with masses on the order of that of the Sun, the kind that form when 2 massive stars collapse under their own weight. But if the black holes are too big, LIGO can't see them, and there are lumbering, rumbling, behemoth black holes out there that escape LIGO's sight. Observational evidence suggests that nearly every large galaxy contains a black hole at its center, millions or billions of times the mass of black holes that LIGO can see. These black holes do not form from stellar collapse like the LIGO black holes, but by merging with other galaxies. And galaxies are merging all across the universe, and when they do, so do the black holes at their centers, forming supermassive black hole binaries. But here's the key thing that make gravitational waves from these supermassive black hole binaries different than those detected by LIGO. Because these supermassive black holes take millions of years to merge, there's not just one pair merging at a time. There's not even a handful merging at a time. No, the combined gravitational waves of all of the supermassive black holes merging over cosmic history of different sizes and frequencies add together to form a low-frequency hum of gravitational waves, a gravitational wave background. Here's an analogy that I think might help. Imagine you're eating lunch in a crowded cafeteria. You can hear the conversations of your friends at your table because they're close by and therefore appear louder. But you can't hear the conversations of everyone else in the cafeteria. They just form a loud background hum. Your friends are the individual sources of gravitational waves, the individual supermassive black hole binaries. Observations with good old light detecting telescopes suggest that everyone else in the cafeteria is the gravitational wave background, the sum of all of the gravitational waves from all of the supermassive black hole mergers across the universe. Now, what we've actually seen by measuring the gravitational wave background before any individual sources of low-frequency gravitational waves is that the background hum is so loud you can't hear your friend's conversation. By studying the statistical properties of this background hum, we can begin to understand the history of supermassive black hole mergers and, by proxy, galaxy evolution history across cosmic time. And this is only the beginning. Maybe we'll find that the background is quieter than we expected at lower frequencies, giving us a glimpse into the chaotic interactions between these gargantuan black holes and their environments. Maybe we'll find that the background hum contains more shrill tones than we expected, suggesting possible contributions from exotic sources of gravitational waves, like cosmic strings or quantum fluctuations in the early universe. But measuring this background requires some creativity. These supermassive black hole binaries take years or decades to complete one orbit, producing gravitational waves with wavelengths of light years. A miles-long gravitational wave detector like LIGO can't possibly hope to detect such long gravitational waves. If only we had lasers being beamed to us from light years away. Fortunately, nature has provided these for us. When a supergiant star, about 20 times the mass of the Sun, runs out of nuclear fuel, the pull of gravity becomes too strong and the star collapses under its own weight. The pressure at the center of this collapsing star is so great that the electrons get forced into the nucleus of their atoms. If the core of the star can stave off total collapse, the outer layers will rebound off the core, flung into interstellar space in a supernova explosion. What's left of the core is a ball of neutrons the size of a small city, a neutron star. In the collapse, the star must conserve its angular momentum, like a figure skater pulling her arms in to spin faster and faster. Neutron stars are spun up to incredible speeds, some rotating faster than a kitchen blender. The magnetic fields of neutron stars are so tremendous that they accelerate charged particles toward the magnetic poles of the star at nearly the speed of light, generating beams of light. If these beams are not aligned with the rotation axis of the star, they swing around like stellar lighthouses. We have a special name for neutron stars whose rotating beams intersect with the Earth. We call them pulsars. Pulsars emit only very dimly in the visible light that can be captured by human eyes or optical telescopes. Instead, these beams are comprised of radio light, which is invisible to humans. Radio light is the lowest energy of all of the light produced in the universe, which is why we use huge radio telescopes to observe pulsars. Instead of seeing the star itself, our radio telescopes see a pulse every time the beam points toward Earth. By measuring the arrival times of these pulses, we can monitor changes in the distance between the Earth and the pulsar, kind of like the laser arms of LIGO, but on a galactic scale. And some of these pulsars blink at us with atomic clock level precision. On short timescales, if nothing in the space between the pulsar and the Earth changes, the time between each pulse doesn't change. They arrive regularly. However, if the distance between the pulsar and the Earth decreases, the pulse will arrive earlier. And if the distance increases, the pulse will arrive later. Now we have a super accurate timekeeper to keep track of the changing distance between the Earth and the pulsar. We're ready to detect gravitational waves, right? Unfortunately, lots of things besides gravitational waves can change the distance between the Earth and the pulsar, like the Earth going around the Sun or the pulsar orbiting a companion star. So to tease out the dance of gravitational waves, we need more pulsars and we need them spread across the sky. I hope you've been practicing the gravitational wave dance because now we're going to need it. So once again, I want you to imagine that there's a gravitational wave passing from behind me, through my body, and out of your screen, from back to front. And I am oriented in the up-down and left-right directions. But this time, I also want you to imagine a ring of pulsars around me, and the Earth is at my center. This is our galaxy of pulsars. What's going to happen to the pulsars when the gravitational wave passes? Well, when the trough of the wave passes, my galaxy of pulsars gets short and fat. And when the peak of the wave passes, it gets tall and skinny. As the gravitational wave passes, the distance between the Earth and the pulsars changes in this very specific way. How does that affect the pulse times of arrival? Well, when the peak of the wave passes, the pulsars above and below the Earth get further away, so their pulses arrive later than the pulsars on the left and right, which have moved closer. And when the trough of the wave passes, the pulsars above and below get closer and their pulses arrive earlier. This is the way that gravitational waves are encoded into the pulsar signals. This is our galaxy-sized gravitational wave detector made out of stars, also known as a pulsar timing array. Now that you're all expert dancers, you can finally understand this exciting discovery. On the vertical axis is a measure of how similar the pulse times of arrival are for a pair of pulsars in the array. So if the arrival times are changing in the same way, you get a high value. If they're changing in opposite ways, you get a low value. On the horizontal axis is the angular separation of two pulsars. So if two pulsars are separated by 0 degrees from each other, they're right next to each other on the sky. And if they're separated by 180 degrees, they're on opposite sides of the sky. So for two pulsars with 0 separation, how do they move due to a passing gravitational wave from back to front? Well, that's this part of the dance. They move in the same way as the gravitational wave passes, and their pulse times of arrival are affected in exactly the same way. So this graph is at a maximum. What about two pulsars separated by 90 degrees on the sky? Well, that's this part of the dance. These pulsars are moving in completely opposite directions, and when one is closest to the Earth, the other is furthest. Their pulse times of arrival are affected in the complete opposite way, so this graph dips to a minimum. How about two pulsars on opposite sides of the sky? Well, that's this part of the dance. They're moving closer and further from the Earth at the same time, but in opposite directions. So their times of arrival are affected in a similar way, but not exactly in the same way. So this graph comes halfway back up. This is a graphical representation of our dance. Seeing this trend in all of the pulsars in our array is the evidence we needed to know that we're seeing the gravitational wave background. And these are our data that we've just published. These dots are pairs of pulsars in the NANOGrav pulsar timing array. We're so excited because 15 years of data and observations revealed that all of the pulsars are doing the dance. And astronomers in other countries with their own independent pulsar timing arrays are also seeing evidence of this dance. And this is only just the beginning. So many questions are yet to be answered. How do supermassive black holes evolve? Will an individual supermassive black hole merger pipe up above the background? Are there exotic sources of gravitational waves yet to be discovered? This new way of viewing the cosmos can help us answer these questions. In the next video, we'll take a closer look at how to time a pulsar and the radio observatories we use to do it. I hope you'll join me. Until then, thanks for watching. This video was made possible thanks to NANOGrav, a physics frontier center of the National Science Foundation.